We're going to do some problems in section 3.7. Number 20, it says we're supposed to write any rational function, and a rational function for having these asymptotes. So therefore the function would have to have, in the denominator, to have a vertical asymptote at -4, it'd have to go x plus 4. Because -4 plus 4 would be 0. It can't be division by 0. And would have to have 1 at x plus 1. And if it's got an x-intercept at 1, that means the numerator's got to have x minus 1. If the numerator, if I put in 1, I get 0, and 0 in a fraction makes the whole thing 0. So that's an x-intercept. And also at 5. And to go through 7, I'm going to have to multiply maybe by something. And to find out what that something is, I'm going to put 0 in for all the x's, and I have to come up with 7 for the y. So 7 equals a times, if I put 0 in there, I get -1, times 0 in there, I get -5, over 0 in there, I get 4, and 0 in there, I get times a plus 1. So this is 5 over 4. So this is a times 5 over 4. So I would multiply both sides by 4/5. And so 28 over 5 is what a has to be. So right here would have to be 28 over 5. And that would complete that rational function. Okay, let's do 24. It says it has a vertical asymptote at 3. So f of x would equal some a and then x minus 3. I'm messing this one up. Not thinking here. F of x would be a rational function. There would be an a, and the denominator, vertical asymptote has to be in the denominator, x minus 3, and a double 0 at 1, so that would be x minus 1 squared, and a y-intercept of 4, so if I put in zeros, I'm supposed to get 4 equals a times, if I put in 0 here, I get -1 squared, which is 1, and minus 0 in here, I get -3. So I'd have to multiply both sides by -3, and a would equal -12. So I'd have to put -12 in for the a times this, and this would have this desired look. It will have an oblique asymptote because the degree of the numerator is greater than the denominator. But that's not a problem. Now we're supposed to write equations for these, and one of them I assigned was 28. So, doing the same kind of things, we just have a picture now to tell us. It's got a vertical asymptote at -3, so we got x plus 3 in the denominator. A vertical asymptote at +4, so we'd have to have x minus 4 in the denominator. And it both go in the same direction at this one, so this would have to be squared or to the fourth or to the sixth. This could be cubed or just 1, 3, 5, or 7. Now the numerator has to have an a. Then it might be 1, but we'll see here. And it crosses at +2, so it's x minus 2, and that appears to be the only x-intercept. Now to find the a, it has a y-intercept of 1. So if I put 0 in for the x's, I'm supposed to get 1. And this, if I put 0 there, I get -2 over 3 times 16. 3 times 16 is 48. 2 over 48 is negative 1 over 24, reducing it. So I multiply by negative 24 on both sides. And that will get rid of the 24 and the negative. So I need to put negative 24 here to make this go through plus 1. Okay, let's go to 30. Now, this one's got less to it. It's got a vertical asymptote at minus 2. So the denominator would have to have an x plus 2, either a single or a triple, because they go in opposite directions. And in the numerator, it crosses at x equal negative 4, so we've got to go x plus 4. And it crosses at 1, so we have to do an x minus 1. And now the degree of the numerator is more than the denominator, so it would have an oblique asymptote, which this does. And we'll put an a. We need to go through 1, so let's figure out what a is. When x is 0, we're supposed to get 1. So I'd have a times 4 times negative 1 divided by 2 is supposed to equal 1. Well, let's see. 4 times negative 1 is negative 4. Divided by 2 is negative 2. So divide by negative 2, and a will be negative 1/2. That's what would go in for the a. And then I would have my function, and it will have the oblique asymptote, slant asymptote. Let's do 30. This has a horizontal asymptote, so the degree, and it looks like it's 0 because this is coming down and this is going up. So the degree of the numerator has to be less than the denominator. Okay, so let's look at this one. F of x. In the denominator, I need to have, it's got a vertical asymptote at minus 3, so I got to go x plus 3. And it's either out to the 1 or 3 or 5. And here it's got plus 2, so I got to go x minus 2. And they both go in the same direction, so I got to square that. And then in the numerator, I've got plus 1. It bounces, so it's got to be x minus 1 twice. And now the degree of the denominator is 3, and the numerator is 2. So I am okay. That will go to 0. So the horizontal thing is okay. I just need to figure out a, so this goes through 1/2. So when x is 0, I'm supposed to get 1/2. And so I'd have a times 0 minus 1 squared is 1 over 3 times negative 2 squared is 4 times 3 is 12. And I'm supposed to get 1/2. So a would have to be 6 times 1/12 is 1/2. So 6, or multiply both sides by 12. And 1/2 of 12 is 6. So 6 would go here, and that would be the equation. And now let's do this one. Looks fairly simple, but it's got a hole, and it's got a horizontal asymptote that's not 0 but 1. So that means the degree of the denominator and numerator have to be equal, and the leading coefficients have to be 1. So let's start writing this. Let's see, we got a vertical asymptote at minus 1, so it's x plus 1 in the denominator. We got an x-intercept at 2, so it's x minus 2 in the numerator. And this will have, since the numbers in front are ones, it will have a horizontal asymptote at 1 because they're equal degrees, so that's okay. We just got to get a hole in it, and that means at 4, the numerator and denominator both have a factor. So I got to put x minus 4 and x minus 4, and that will make that graph, and it will have a hole there. We can check. If I put 0, I should get minus 2. If I put 0 here, I get minus 2 times, and 0 here times negative 4 over 0 here would be 1, and 0 here would be negative 4. The negative 4's cancel, and it goes through minus 2. Okay, the degree of the numerator is 2, the degree of the denominator is 1, so this has an oblique asymptote, and they want us to find it. So we divide the denominator into the numerator. So I'd go 2x plus 1 divided into, put these in order, minus 2x squared plus x plus 5. 2x times a negative x, or negative 1, 2 times negative 1 makes negative 2, and x times another x would be x squared, so I'm going to start with negative x. Negative 1x times that is negative 2x squared. Negative 1x times 1 is negative 1x. I draw the line and change the signs, and I get 2x plus 5, and now I got to 2x times what makes this, and that would be plus 1, and 1 times this would be 2x plus 1, and I can draw the line and change the signs and add and get 4, but I don't really care about the remainder because that will go to 0 when x gets really large. Here is the equation of the slant asymptote. It's got a minus 1 slope, goes through plus 1 for this one. Now for this one, we'd have to see the degree of the numerator is 1 more than the denominator, so we divide the denominator and the numerator, get it. So we got x squared plus x plus 1 divided into 2x to the third plus x squared plus x. I guess I'd have to take that times a 2 and an x to get 2x to the third. So it's 2x times that is 2x to the third. 2x times x is plus 2x squared. 2x times 1 is plus 2x. Draw the line and change the signs and add like terms. These are like terms, and it's negative x squared. Like terms here come out negative 1x, and x squared times negative 1 will make negative x squared, and I can take the negative 1 times all of this, but I don't really need to, because that will cancel this, and it tells me y equals 2x minus 1 is the oblique asymptote, the slant asymptote for number 44. And I could graph it and check it. 44. Now the book has one way of showing how to do this problem. If you look at online at the solutions for this section, it talks its way through doing this problem. I'm going to do it a little different. Okay, and they say this is the model. I'm going to not use that one and show that you get almost the same answers. Now they say that there's a room, and I'm going to say here's the door to the room, here's the long hallway they talk about, and this is the room here, and they say when you're way down the hallway, the intensity of the Gauss meter, the intensity of the magnetic field, is at 0.2, somewhere way down the hallway. And then when you go into the room, and I'm going to put my y-axis there and my x-axis here, so I'm going to say the room door is at 0. So if I go 6 feet in the room, I'll be at -6, and the reading is 2.3. And if I go to 8 feet into the room, I get, so that'd be -8 on my setup, it's 4.4. And they ask, where is the magnet? And write an equation. So I'm going to plot these points, and I'm going to do it on Desmos. So I'm going to get my computer out here, and let me load up Desmos. Should have done this already, but I didn't. And type in Desmos, and here's my graphing calculator, and my points are, to get points, I'm just going to type X. Then I'm going to say, let's do a table. And let me turn this up so I can type easier. And I'll turn my camera. So now you can see my table. I'm going to change the X that it puts here to a Y. And I want to put, it said way down the hallway, so I'm going to put 20. It was 0.2. Then it said just inside the room at 6 feet, so at -6, it said it was 2.3. And then it said at 8 feet in the room, it was 4.4. Now this, let's get rid of the X. We don't need that anymore. There are the points. There's the one way down the hall, and these. Now this should remind you of the lab we did, and we would have to make y equal, and it has no x-intercepts, so we'll just put an a in the numerator, divided by, and in the denominator they say it needs to have a vertical asymptote on this graph, a vertical asymptote, and I don't know where, so I'm just going to write it at x minus b. So I don't know where to put it. Now it says I can make sliders, so I'm going to do all. So now I can adjust a to different values, and if you look at the graph as I move a, you can see what it's doing. And I can use b, which is going to move the graph sideways. So I'm just sliding the b to make that happen. So let's get this a little further out so you can see more of what I'm doing here. Okay. So this is getting really close to 0, like it should have been out here. And notice it's not bad. It's close to hitting that point. But I need to move this so it hits these other 2 points that they gave us. So I'm going to slide my B so that it moves it over closer to these. But now you can see that the shape is not quite right, so I'm going to adjust that a little bit. And that's getting closer. It may not be going far enough, but we'll see here. I'll move B so I move it back some more. Oh, that's getting really close, isn't it? So right now, I'm not bad at all with this graph. Looks like I need to go a little bit more than -10. So I'm going to go click on that -10 and say I want to go to -15 to 0. And I'll just make it step at 0.1. And so now I can slide this further over. And that hits those 2 points pretty nicely. And if I look over here, it's a little bit high, but not bad. I can move it down by changing A, but that messes it up over here. So I'm just going to leave it through these 2 points. And it looks like it works pretty well with A equal 10 and the denominator having -10.3. So what I found is that I have an equation that's y equals A was 10 over B equal x, the denominator being x plus 10.3. So that's my equation. And now they asked for, let me just so you can see that. That's the equation that I get. And they asked, give a rational model. Well, I've given a little bit different looking one than the one they gave. And how far must he go to reach 10? So I'm going to bring the computer back, and then how far do I have to go, how far must he go for the meter to reach a reading of 10 and the meter to reach 100? And then we're supposed to figure out where the magnet is. So let's go first to what will the meter, where would we have to be to get 10? So let's zoom in here. There's 10, and if I'm on the curve right there, it looks like I'd have to be in 9.3 feet into the room. Oop, you can't see it. I'd have to be, get back onto 10. I'm moving up on the graph here. Let me just slide this over here, move the camera this way, and then let's look. I want to see where the curve is 10, and so I'm clicking there, and it says about -9.3 feet into the room is where it will have a Gauss reading of 10. Now I think they had -9.1 feet on the way they did it. And then they want to know when it's 100 and how far in the room would we have to be. And to be 100, got to get up here to where there's 100. I could have squeezed it, but I'm just going to do 100. And it says I need to be in the room about 10.2, -10.2. Reasonable answer for the data we have. And it looks like it's going to get really strong at this vertical asymptote. Well, the vertical asymptote is going to be at 10.3 feet into the room. And that would be my answer for that problem. Okay? Now we could do it with their adjustments and make it a little bit more adjustable, but this works well for what we have. Okay?